Hey everybody, let's see, so we're, I think, mid to beyond midway through chapter 20 now, and as you know, it's kind of like just hashing and rehashing all of the carboxylic acid derivatives, right? And we're on number 7 right now, chemistry of esters, and the conceptual details are in the PowerPoint. This is all from last time. A was how to make esters. There were 3 methods. You know, all from review, it was the acid chloride method, the Fischer esterification method, and the SN2 method also. That's kind of a new way to making esters for you guys, but they're all easy. I'm not going to review them all because it's all in the last PowerPoint, but we went through all of this last time. Let's see. We did the SN2 method, and then once you know how to make esters, then we talked about all the reactions of esters, including hydrolysis of esters. And there were kind of like 2 methods to hydrolyze esters. There was the saponification, which is base mediated, and then there's the acid catalyzed hydrolysis of esters, right? And we talked about how base-mediated hydrolysis worked. It was just a NAS reaction with hydroxide, just kind of attacks, and then you kick off methoxy as a leaving group, and then it's all in equilibrium, and then methoxide takes the proton to make a carboxylate. And this was a irreversible reaction. And that was like kind of what drives the whole equilibrium forward, because it's like, oh, you have equilibrium, and then you have an irreversible reaction, and then it just grabs. Then the next step ensues with H3O, and you grab a proton from acid water. But then there was also, this is base mediated. We also have acid catalyzed, and that's like just the opposite of the Fischer esterification method, right? That's I think this. I think we already had you step through this mechanism before. It's really easy, protonation, and then the RSCC, and then the water attacks, and then proton transfer, etc., etc. All right, so that's just the acid catalyzed hydrolysis of esters, right? Okay, so then we also did learn about NAS, converting esters to amides. That was really boring. I'm not going to really say anything else about it. You can, those in your last lecture notes. Reaction with organometallics. This was less boring. I think it's actually really cool to use organometallics to make CC bonds, right? These are CC bond forming reactions. You could use Grignards, you could use organolithiums. The big thing was that the Grignards and organolithiums add twice to esters. They add once, you get a ketone, then it adds again, and then you get a tertiary alcohol. Cuprates do not react with esters. Okay, what do cuprates react with? What's the derivative that cuprates react with? And that was acid chlorides, right? So cuprates only react with acid chlorides in terms of the stuff you're going to see this chapter. And when they react with acid chlorides, they react once, whereas these guys react twice. Okay, all right. But when with reducing agents like hydride reducing agents, depending on which reducing agent you use, you can either get a double reduction to a primary alcohol or a single reduction to an aldehyde. And that was, so esters do have that option for reduction. Okay? And yeah, as we learned, the hard reducing agent, the highly reactive reducing agent, lithium aluminum hydride, does a double reduction where it first makes an aldehyde and then it reacts a second time, because the aldehyde's even more reactive than the ester, and so it always goes to a primary alcohol with lithium aluminum hydride. And then as we we explained last time, we can do this partial reduction, and that means just like stopping at the aldehyde, right? Using a special reagent called diisobutyl aluminum hydride. There's three names for it that are commonly used. There's diibol H. There's probably even more names actually. Diibol H. Sometimes you just call it diibol, or diba. Some books use all of these different things to mean the same thing, and it's just a reducing agent that stops at the aldehyde. It's a partial reducing agent of esters. For now, just esters. There's going to be other things it reduces also. It's just a different hydride, it's different H-, and the big thing was that you would make this temporarily stabilized tetrahedral intermediate that stops. When we say it does not collapse, what do we mean by that? It means that this is stable. This is not like the O- kicks down and kicks off the ethyl. It just kind of stops. And when it stops, it can't be reduced anymore, right? It's like stuck in this situation until you add acid water, right? And then that destroys the diibol, any excess diibol, like destroys the reducing agent, and then it allows this thing to collapse, and then you get the aldehyde. That was kind of the cool mechanism for how diibol works. Alright, so we're on seven. We're still on number 7 now. Esters. Yeah, esters, like I said before, is kind of a big topic because there's a lot of reactions that you can do to esters. All right. Next one is F, and this is a pretty easy one. Alkylation of ester enolates. Alkylation of ester enolates. What does that mean? Alkylation probably means we're attaching an alkyl group, like a methyl or a ethyl or a propyl. Ester enolate. Any guess what that means? It's just an enolate of an ester, right? And we did a whole chapter on enolates, but it's usually like ketone enolates and aldehyde enolates, right? Well, anyway, so this is a pretty simple idea. It's just that if I have an ester, and we're going to use this cyclic ester. I may have mentioned that cyclic esters have a name. They're called lactones. A lactone or lactones. That if we take this ester and we want to attach something at the alpha position, like a propyl group or something, how can we do that? Well, rip off the proton on the alpha position, make it a nice nucleophile, and then attack like propyl with a leaving group, right? Usually it's something primary, so like propyl bromide, 1-bromopropane. Okay, so need a couple reagents. We need, well, step 2 is easy. It's bromopropane, 1-bromopropane, right? We need an appropriate base to rip off that proton, and the pKa of the proton is about 25. pKa equals 25. And that's not, I mean, we have a lot of range of acidity, right? But that's, you know, what's a ketone? A ketone's roughly about 20. 20 or so. And so this is just a little less acidic, but we do have a good, pretty universal superbase that will take off a proton, almost anything under 30 almost, and that's LDA, right? LDAs are one of our super bases. So LDA, of course, the structure is nitrogen with 2 isopropyl groups, negative charge, and like a lithium. This stuff's called LDA, right? We've seen it multiple times now as a very strong base. It loves to be a base, not a nucleophile. It doesn't go attack stuff as a nucleophile because it's got 2 big isopropyl groups, so it's very sterically hindered, right? Anyway, so it's a base. It's a wonderful base for almost any type of carbonyl, like ketones, aldehydes, esters, nitriles, other things that we're going to see. And as a base, what do bases do? Bases take protons, and so it's just going to make this ester enolate. It's just an ester enolate. Okay, it's just an enolate of the ester. And now this is super easy. It just swings down, and the enolate alkene essentially attacks the carbon, kicks off the Br. And what kind of reaction from organic 1 is that? Nucleophile attacks the carbon, kicks off leaving group. That's an SN2 reaction, right? Okay. Yeah, that gives a product. So in terms of mechanisms, this is almost as easy as it gets. Typically, with these kind of reactions, it's a good nucleophile, but it's also kind of a good base. Remember the competing reaction with SN2 reactions, where from organic 1 there's like SN2 and then something else too, and the E2 is the competing side reaction. And if this is kind of sterically hindered, you might get an E2 reaction. So what I'll just say is the alkyl halide should be methyl or primary. To eliminate potential E2 reaction. We've seen that restriction before also with other kinds of SN2 reactions. If you have a basic nucleophile, usually you need methyl or primary. You can't use like secondary or tertiary without potentially getting E2 reactions instead. Okay, so yeah, that was easy. Alkylations of ester enolates. Alright. G. G is esters in nature, food, and cell membranes. This was done in the PowerPoint, so you already saw this. I think in the textbook they show it right now, but we did all that earlier in the PowerPoint. H is spectroscopy of esters. That's also done in PowerPoint. Alright, so yeah, cool. So a lot of that stuff is done in PowerPoint. Okay. Alright, so now we're on to number 8. We're wrapping up the chapter slowly. Still got some fun reactions to talk about. Chemistry of amides. So we're kind of going down the list of carboxylic acid derivatives, and now we're on to amides. Alright? So amides, of course, are things that look like this. You either have one R group on the nitrogen, or 2 R groups, or even 0 R groups, like it could be an NH2. All of those are amides. So, following our little pattern, first thing we're going to talk about is how to make amides. And this is totally easy because you know about it. You know how to make amides. One way is well, it's a typical way to make amides is from more reactive derivatives. More reactive derivatives. What does that mean? What's a more reactive derivative, carboxylic acid derivative, than amide? Remember our little chart? Acid chlorides, anhydrides, esters, amides, carboxylic acids, right? So anything to the left on that chart is more reactive. So I think we introduced chapter 19, you know, and the NAS reaction by talking about how carboxylic acid chlorides, or just acid chlorides, can be converted to any of the derivatives. So if I want to make an amide, I can start with an acid chloride. That's super easy. And what's our base that we usually use? Like pyridine or something. PYR dot dot. Sure, that'll make an amide. Cyclic amide with the nitrogen in a 6-member ring, like that. Of course, this is all NAS, base mediated NAS. That's one way you can make an amide. Another idea, like if you want to make a acetamide, you could. Acetamide means acetyl CH3. Acetamide. Well, we could totally use like an acetate source, right? Acetate source. We could either use acetic anhydride, which is actually the preferred method. Maybe some pyridine in there as a base. We could also use acetyl chloride. Yeah, those are pretty nice ways to make amide like that, an acetamide. Okay, it's also base mediated NAS. Sweet. Okay, so that's an introduction on how to make amides, and you know all this stuff. You've seen it 1,000 times by now. Okay, so now we know how to make them. Let's do some reactions of amides. And remember, we were talking about the order of reactivity, and we said, you know, acid chlorides, anhydrides, esters, amides, and carboxylic acids. So what's to the right of an amide? What's to the right in terms of reactivity? Only carboxylic acids, and so carboxylic acids are we can convert an amide to a carboxylic acid pretty easily, right? In terms of the leaving groupability, everything makes sense to turn an amide into a carboxylic acid. Okay, and when we do that, it's called hydrolysis. So one reaction we can do. And you know, first we learn how to make them, and then we learn how to what are the reactions that we can do of these things. One reaction we can do of an amide is called hydrolysis, and that just hydrolyzes it to a carboxylic acid. Now this is kind of a harsh reaction, and I say it's very harsh, and that is because an amide is actually a very, very stable functional group, and it's a little difficult to just cleave it by using acid water or base water. So it's actually, this is not what we consider an easy reaction. Okay, so it's a little harsh, but we can do it. One way to do it is acid catalyzed hydrolysis, kind of like acid catalyzed hydrolysis of an ester. And it's actually, we can even draw it the same way that we draw acid catalyzed hydrolysis of an ester. So we're going from A plus B to make C plus D, and you probably use excess water when we're doing this, so we're just going to force it. We're going to force hydrolysis. But you usually need a lot of heat, exclamation point, exclamation point, exclamation point. And usually a lot of time, so you might have to like boil it in acid for like overnight or something like that. The mechanism is really easy, and I'm not even going to do it. Easy mech, like ester hydrolysis, right? So you could do this if you want practice. Essentially, you would just start by protonating the C double bond O, and then you would make an RSCC, and then water would attack it, and then proton transfer to the leaving group. Nitrogen's going to be the leaving group, and then kind of kick it off. Nevertheless, it is a harsh reaction because of the stability of the functional group. And there's a lot of resonance stability in the amide that we talked about. Okay. Okay, so 8 is amides, and we're on reactions, hydrolysis. Another thing you can do is base-mediated hydrolysis instead of acid catalyzed hydrolysis. And so if I have an amide, I can treat it with like sodium hydroxide and then acid water, just like I did with esters. And so it's the same thing. It's like saponification of an ester, where sodium hydroxide attacks and electrons go up. And I'm just going to say it's the same exact mechanism. C saponification mechanism. And there's also not saponification of ester. It's also like not what I consider an exciting mechanism, so probably not something you're going to see on the quiz. But if you want practice, yeah, this attacks, and then electrons go up, and then the electrons kick down and kick off nitrogen, and then there's that the base, NH minus, would take the proton off the carboxylic acid. And so actually the last step is irreversible. But if you look at saponification, you'll see what I'm talking about, because it's the same exact mechanism for base-mediated hydrolysis of an amide versus base-mediated hydrolysis of an ester. Okay, so it's like equilibrium, and then we have an irreversible step to the product, or maybe a couple irreversible steps. Anyway, not an exciting reaction, but yes, it is possible to do a base-mediated hydrolysis of an amide. Okay, now we're moving on to the more cool stuff, I think. Reactions, reduction of ammides. Reduction and I'm going to put a couple stars here. This is like some pretty kind of cool and unique chemistry applied to amides. Okay, and there's going to be two ways that we can reduce amides. Alright. Okay, and the two ways are going to be H minus 2 equivalents, just like with esters. Remember how we did this for esters? We can reduce with either H minus 2 equivalents, or we can do what? H minus 1 equivalents. Okay, and so I'll give you a hint on what the two reagents are, and we'll show how they work. Okay, what do you think H minus 2 equivalents is going to be? Think about what was H minus 2 equivalents for esters. how did we do a double reduction of an ester? What was the H- reagent for esters? It was lithium aluminum hydride. And there's like an acid step or whatever. Now, and then for H- one equivalent, what was it for esters? Because it's the same thing for amides. It began with D. Remember, something D, blah, 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 blah. It was dibol. Dibol H, dibol H, or dibol, DIBAH. We had all those things. Alright, so we have two different ways we can do reductions of amides. Alright, so let's show those now. I'm going to first show the lithium aluminum hydride method. Okay, so let's show the lithium aluminum hydride reduction of an amide first. I'll draw an amide. Miscellaneous amide. And the reagents are lithium aluminum hydride and usually a little bit of water or acid. Okay, and what I'm going to do is I'm not going to show the product. We're just going to do the mechanism, and then we're going to wrap our way to the product, because the product is a little bit weird, and I don't want to give it away because it's a little weird. All right, so what's the mechanism for all of these reactions? When we have lithium aluminum hydride, we got what do we abbreviate that as? What's the abbreviation for lithium aluminum hydride? Mechanistic abbreviation. I say double quotes. H dot dot minus double quotes. So it's like, it's, you know, basically nucleophilic hydride. I might even write nuke underneath. Like it's like nucleophilic hydride, right? And what does nucleophilic hydride do to that amide? Well, it attacks it. Where's it going to attack it? Delta minus, delta plus. Yeah, the negative attacks the plus, right? So it does what we did for esters also. Okay, so it attacks and electrons go up. Nothing crazy, it's the same as esters so far, right? Okay. We got our O minus, we got our H, we got our nitrogen with a pair of ethyl groups on it. Alright. I gotta draw some more stuff, so hopefully you're not as congested, your drawing is not as congested as mine, but what I need to draw a counterion for oxygen. It's something like, I just abbreviated AlX2 plus. AlX2 plus. AlX2 plus. That's a pretty good counterion. Alright, it's something like that. You know, there's some hydrogens, and the exact structure of it's not that important. But it's definitely aluminum, it's definitely positive. It's got some stuff on there. Alright? Okay, and now when ester, think about what happened with esters. At this point, if you had an ester, like say this is O-ethyl, like a ethyl ester or something, right? What was the next step? Like we had ethoxy over here. In the next step, when you had an ester, oxygen swings down, kicks off the ester, right? The ethyl. And then you have an aldehyde, right? You have an aldehyde, and then the aldehyde gets reduced, and you get an alcohol, right? That was the whole thing about a double reduction of an ester. You go from an ester to an aldehyde to a primary alcohol, right? Alright, so you think the oxygen swings down and kicks off this thing. And that is where it's different for an amide. So it's not this way. It's not the oxygen kicks off the nitrogen. It's actually different now. The nitrogen kicks off the oxygen. So it's going to be a little different, and that's going to give you a different product. So the nitrogen decides, no, you're not going to kick me off, I'm going to kick the oxygen off. So the nitrogen kicks its electrons in, and this whole thing up here basically acts as a leaving group. And you know, it's a little, I mean, leaving group ability is sometimes a little weird, and I don't really understand why this is a good leaving group, but it goes away. And it probably, the oxygen talks to the aluminum, oxygen loves aluminum. Yeah, so there's maybe some covalent nature here, but the big thing is nitrogen kicks off oxygen. All right, what does that give us then? Same molecule. Got an ethyl and an ethyl. Any charges? We have the H. We added an H, right? There's the H we added from before. I just flipped it over from the bottom to the top. Any charges? Is that a nice happy molecule or neutral, negative, positive? Well, the nitrogen gave up its lone pair, so it's positive, right? And this has a name. Think back chapter 17, I think it was. You know, if you had this, let's just pretend we have that. What would that thing be called? That would be called an imine, right? It's C double bond N. C double bond N, and then you have like an ethyl group, right? That would be an imine. Imine, I-M-I-N-E. But when you got two ethyls and you got a positive charge, it's not an imine anymore. It's a, anybody remember? I'm talking to you like you're all in a classroom right now. What is it? It's not imine, it's almost imine. It's iminium, right? Iminium. Iminiums are these positively charged imine type things. And they are electrophilic. They love to be attacked by nucleophiles. And so now H dot dot minus attacks again. And put it in quotes because it's not exactly free H dot dot minus. It's just the mechanism is easy if we just say that. And where's it going to attack? It does not attack the nitrogen because that would be a violation of the octet rule. It attacks the carbon because the carbon is electrophilic and it's actually an RSCC. We could draw the RSCC, and you know, if you want to do that, go for it, where you kick the electrons onto the nitrogen and then you have a positive charge in carbon. You can totally do that if you want. I'm going to be lazy and just have this attack and kick electrons onto nitrogen. And what does the product look like? The product is now essentially HH here. Right? We added one H, we added two H's. So there's the two H's we added are there, and they basically replace the double bond O. And I'm just going to erase those because we know where they are. And now you can really see what the difference is between starting material and product. It simply removes the double bond O. That is what the double reduction of an amide looks like with lithium aluminum hydride. Alright, so lithium aluminum hydride does different stuff if it reacts with an ester. It just makes a primary alcohol, right? But if it reacts with an amide, it makes an amine. It makes a amine. It just wipes off the double bond O. That's what lithium aluminum hydride does to an amine. Okay? All right. Okay, so that is our H dot dot minus 2 equivalence reaction with amides. Is basically loss of the C double bond O. All right. Next. Now we're going to do the H dot dot minus 1 equivalent reaction. What was the reagent for H dot dot minus 1 equivalent? It's not lithium aluminum hydride. It's actually the same reagent we used for esters as dibol. dibol or dibol H or dibol, and like some kind of acid intermediate. Okay, now this does the same exact thing as esters, what we did with esters. So this is, we don't have that weird behavior that we just saw when we react amides with dibol. It actually just makes the ester, sorry, the aldehyde. And then you get your amine as a byproduct, diethylamine, whatever. Okay, so this is going to be the byproduct, diethylamine, there. Okay, alright, so, and then this is actually works exactly the same way the ester reaction did. So that's convenient. We can just do the mechanism real quickly. So dibol is just a different H- source. Remember the structure of a dibol? It was aluminum hydride and 2 isobutyls. Those are whoa, screwed up. A pair of isobutyls on your aluminum hydride. Okay, so what was the reaction, and how did it work with esters, and how does it work with amides? It's the same exact thing. So circle the hydrogen, it kicks electrons up. Got your ethyls, got your hydrogen, and just like with esters, we say AlX2. It's a different AlX2, and it's the X's are probably isobutyl groups. But this thing, just like with esters, is temporarily stabilized. And by temporarily stabilized, I mean it does not kick off the oxygen, nor does nitrogen kick off the oxygen. Sorry, oxygen does not kick off nitrogen, nor does nitrogen kick off oxygen. It's stabilized. It's actually just, it stops here. This is like where it stops. Okay, until you treat this with acid, which is the second step of the reaction. And then H3O first destroys any remaining hydride. Any H- you have left over reacts essentially with H+. What do you get if H- reacts with H+? You get H2, right? You got to do this very carefully because H2 is very flammable, and there's usually going to be H2 plus heat, and H2 plus heat, if you do that wrong, is a big fireball. And so you have to be careful with your when you do this. You usually have some ice or something to cool it all down, and then yeah. But anyway, after H3O destroys the H-, it also protonates the O-, and you get OH. You also get a proton on nitrogen, so it's like a great leaving group. Okay, and then now oxygen swings down, kicks off nitrogen, and we're basically done, and we're almost at that aldehyde product that we need. Okay. I'll draw the amine up top again here, just to declutter. So we have a protonated aldehyde, -H+, lose the proton on the aldehyde, we get the desired product. Okay, we're good, and then that the byproduct, of course, is diethylamine. I'll just draw that up here. Okay. Overall, though, H-1 equivalent, which, you know, the reagent is dibol, converts an amide into an aldehyde. Okay. So that's what happens when you add a single hydride to an amide. Okay. So we're still on amides. And we're on C, reduction of ammons. Okay, let's just show a couple examples of these reactions we just talked about. There's an amide. It's got like a double amide, I guess. I don't know. Whatever. You have two amides. What's the product if you react this with lithium aluminum hydride and water or acid? What's the product? Does this cleave the amides to make like amines and alcohols or something? Or what did we say that lithium aluminum hydride does? It just wipes off the double bond O's, right? It just makes that. It just wipes away the double bond O's. So that's easy. Now you have a diamine. What if we want to turn this into ethyl? How would we do that? How do we build on those ethyl groups given what we know right now, the chemistry we know? Is that possible? Well, we now know that one way to actually make amines, because we just converted amide to amine, right? One way to make amines is you can make amides and reduce them, right? So is there a way we could attach like a 2-carbon piece that's an amide and then reduce the amide back to an amine? And yeah, of course, that's the way we do this, right? How would we do this? Make an amide, make a double amide, turn the double amine, these double amines, into double amides, and the amides will just have 2 carbons and 2 carbons, and then we reduce them. So we just go backwards if we want. No. Yeah. What if we made the double amide? And then those amides could be reduced down to the amines. How do you do that? How do you reduce an amide to an amine? I don't know. What do you guys think? How do you reduce amides to amines? Well, lithium aluminum hydride. Okay. And then, now the only issue is how do we make amides? Because you got to make amides, and it's not a 2-step process, it's just a 1-step process. So we could, typically to do this, you'd either use the acid chloride or the anhydride, acetic anhydride or acetyl chloride. So we could do, this is probably the preferred method, acetic anhydride and pyridine. Of course, nitrogen attacks and the other nitrogen attacks, and then the pyridine's involved in the mechanism. But you can of course use acetyl chloride also. Right, you could totally use this as well. You use acetic anhydride and pyridine, or you could use acetyl chloride and pyridine, and that would make this like double amide type structure. Okay, that was cool. That's a nice application of this lithium aluminum hydride reaction that reduces amides to amines. Okay. Alright, here's a question. How can you, if I have a carboxylic acid, and given all of the chemistry you know now, all of your organic ones, so it's hard for you to think about, like, what all do I know? Is there any way to go from a carboxylic acid to an aldehyde. Carboxylic acid to an aldehyde. And like, if you think about it, that should just be like a partial reduction of a carboxylic acid to an aldehyde, right? Could we add H-1 equivalent? That, you know, kick off 1OH. Yeah, in principle you can do that, but we've never learned that. And when we learned about reduction of carboxylic acids, all I taught you was lithium aluminum hydride. And lithium aluminum hydride does a double reduction to the alcohol. So that's not possible. And I'll give you a hint, this is impossible in one step. But you can do this in a couple steps. So like, how could I do this in 2 steps, for example? How could I go from a carboxylic acid to an aldehyde in 2 steps? Well, one way we could do this is we could do the double reduction that we learned about earlier, lithium aluminum hydride, right? And so I'll say then H2O, actually H3O, right? H2O or H3O. It's 2 steps. But I want to differentiate that reaction from a second different reaction. Because if we do lithium aluminum hydride, that converts the carboxylic acid into the primary alcohol, right? That would make the primary alcohol. And then how do you go from a primary alcohol to an aldehyde? So this is organic 1. 3 letters. It's a partial oxidizing agent based on chromium with 3 letters, begins with P. It's a PCC, right? So yeah, that's one way we could accomplish this. If we need to go from an acid to an aldehyde, do a full reduction and then a partial oxidation, because PCC is a partial oxidizing agent. Okay, and now we know other ways we can do this, multi-step ways. Like what? Do we know other reactions now that we just learned that create aldehydes? Reduction of something to create an aldehyde. Not reduction of a carboxylic acid, but maybe reduction of a ester or an amide, right? Because now we know that if you have an ester or an amide, we can do a single step reduction with what? So what I'll do is I'll say this will make a ester, a methyl ester. How do you make a methyl ester? H plus methanol, right? That's the Fischer esterification. So this would create a methyl ester. And assuming you make a methyl ester, how do you reduce an ester, partial reduction of an ester to an aldehyde? Well, 5 letters begins with D, dibol, right? So that's kind of synthetically how you would accomplish that. Now that uses an ester. How could we not use an ester? Any other ways? We just learned another way. That's not an ester method, but which section are we in right now? We're in the amide section, right? How could we just maybe turn this into some kind of amide and then do a partial reduction? Because you can do that too. I'll just draw it. I'll step through it all. Make an amide. How do we turn this into an amide? Probably make an acid chloride first. How do you make an acid chloride? Because the best way to probably make an amide from here is make it into an acid chloride and then throw in some kind of nitrogen thing, right? So how do you make an acid chloride? Probably from SOCl2, thionyl chloride. Now we just pick our choice on what amide we want to make. Maybe I'll use dimethylamine, so HN. Doesn't really matter. You don't even need purity in here because this is a base as well. So this will do everything. It acts as a nucleophile and it actually acts as a base to absorb the HCl that's being formed. So this is a NAS reaction that makes a dimethyl amide. And how do we reduce the dimethyl amide? Oh yeah, dibol. You always need an acid step after, or water or acid. How do we reduce the amide to an aldehyde? Single step reduction. That's dibol also. Dibol. Unlike water. Actually, I'm sorry. Diol is it is H3O because we need to protonate the. You got to protonate the tetrahedral intermediate thing that we make, right? So I think you actually do need acid for this. Okay, yeah. Anyway, that's cool. So that just shows like a way we can convert a carboxylic acid to an aldehyde through a couple different like indirect methods, either full reduction, partial oxidation, make an ester, and then do a partial reduction of the ester to an aldehyde, or you can make an acid chloride, make an amide, and then do a partial reduction of the amide using Diol. All right, cool. Okay, so now we're going to actually show a pretty cool reaction that has to do with amides, and it's cool enough that we're going to give it its own number. It's going to be number 8. And the summary of this concept, we'll say, is that degradation of primary amides. Alright, and what is a primary amide, first of all? Thinking about amide structure, if you have a R group and an NH2, that's what a primary amide is, because the amide, if you think about the nitrogen, it's only got one thing, which is the double bond O. Now if I had like one R group on here, or like a methyl or something, then it would be a secondary amide. So this is a primary amide. You know, if you have one R group, it would be a secondary amide. If you have two different R groups on it, it would be a tertiary amide. But this only works for primary amides, all right? And this is a pretty cool reaction with a interesting mechanism, and I love interesting mechanisms. So I'm going to put a couple stars there to suggest this is one of the more unique reactions in the textbook. And what is it? And there's a name for it also. This reaction has a name. It's called the Hoffman Rearrangement. The Hoffman Rearrangement. Okay. Yeah, it's a weird reaction. It's got a strange mechanism, but those are always kind of fun for us. Also, my mechanism, mark mechanism, slightly different than textbook. That's okay. It's not a big deal. You can always use my mechanism. You can use the textbook mechanism, like on quizzes and stuff like that. Mine's maybe a little easier to follow, I think, and there's a little less craziness. That's why I kind of like the mechanism that I teach. Okay, all right. So what is it? What's this overall reaction? Let's draw and I'm gonna give myself a lot of space. I'm gonna start way over here. I'm gonna say give myself a ton of space because this is a very crazy mechanism. Not that crazy, but okay. So we have a 3-carbon amide. I'm going to make a huge arrow to the products, which are going to be amine and CO2. That's weird, right? Because how many carbons do we have here? We have 1, 2, 3 carbons on this amide and 2 carbons here. So obviously 3... if I'm going from 3 to 2, I have to lose a carbon or something, and that extra carbon goes away as CO2. All right. So essentially, what's going to happen is that C double bond O is just going to go away as CO2. All right. Okay. So the reagents are Br2, NaOH, and water. Br2, NaOH, and water. Okay. And usually water, or NaOH usually implies water, but we actually use water as a solvent here. Okay, alright, so how's this all going to work? We'll step through the mechanism, And some of the steps are really easy, and then we'll have a couple, maybe one or two kind of weird steps. Alright, so the first step is just simple reaction with base. Okay, and base is probably going to be NaOH, right? So I could write OH minus if I want, or B dot dot serves as base also. Alright, so B dot dot is a base. So what do bases do? They take protons. So a likely candidate for protons to be taken off are the NH2, right? So maybe I'll grab one of those protons and kick electrons onto the nitrogen. Okay? Of course, how many lone pairs do we have initially? We have one lone pair. Okay, so what do we got now? We have C double bond O, we got nitrogen. How many hydrogens do we have left on the amide? We had 2, now we have 1. Draw it kind of over there. And then how many lone pairs do I have on nitrogen now? Because I had 1, and then when I took off a proton from the amide, that leaves another lone pair, so now I got 2 lone pairs. Okay, so we got 2 lone pairs now. Alright, nothing too crazy. Oh yeah, what's the charge? What's the charge? I took a proton off, which is plus, that's left over as negative. So we have a negatively charged nitrogen thing now. Okay, and that is going to act as a nucleophile to Br2, which is almost always an electrophile. Okay, so this is a nucleophile, that's an electrophile. All I'm going to do is swing in and attack bromine. Okay, and attach nitrogen to bromine. Alright, nothing too crazy yet. Got an NH, we got a Br. Okay, all it is it's just a funny amide now with a bromine on it, right? Nothing too crazy yet. Alright, so we have a bromoamide, N-bromoamide. Okay, so now what are we going to do? We're going to do it again. Use more B dot dot. Base, still probably that NaOH, hydroxide. So the base takes this proton. How many lone pairs do we have now? We went from 1 to 2 lone pairs to 1 lone pair. Now base takes this proton off. And that kicks the electrons onto nitrogen. What does that give us? Nitrogen, and still got the Br on there. Now how many lone pairs do we have in nitrogen? We have 2. And what's the charge on nitrogen? Well, just like before, when a base took a proton, where the electrons go onto nitrogen, it is negative. So now it's negatively charged. Okay. All right. Now the first weird thing happens. It's not even that weird, but it happens. We got what appears to be a leaving group, right? Br is a leaving group. If you ever have a leaving group on a thing that's negative, like a negative nitrogen or something like that, a leaving group on an atom that's negative. You've never seen that before. You've never seen a leaving group on an atom that's negative. But if you ever do see a leaving group on an atom that's negative, the leaving group just goes away. There would be a couple other cases here and there where you see that. Leaving group on an atom that's negative, leaving group just goes away. Alright, so what does that give us? Well, Br goes away. Now we have something that looks kind of weird. We've still got those 2 lone pairs. What is the charge of this funny looking thing? Have you ever seen a nitrogen with one thing on it? Maybe you have. I don't. It's pretty rare. What's the charge of it? What's the charge? Well, when I teach formal charge in Organic 1, we always say valence electrons minus dots minus dashes. So it's 5 minus 4 dots, and then minus 1 dash, 5 minus 4 minus 1 is neutral. This is a neutral species. This is a very weird looking neutral species, but it's highly reactive. It's highly reactive. It doesn't have a full octet, for example. There's some other issues with it. And anyway, it has a name too. It's called a nitrene. Nitrene. Actually, acyl nitrene. Acyl means the double bond O. Nitrene means the weird thing, carbon, nitrogen, with these lone pairs. Okay. All right. So then now the first kind of pretty crazy thing happens. This was a little crazy. It wasn't that crazy. This is a little more crazy. All right. So one of the things that nitrenes will do is the nitrogen will kick in, make a double bond N, N double bond C, and now the ethyl group will jump. So that is pretty weird. I hope you agree. So the ethyl group, particularly that carbon, the terminal carbon, or the internal carbon here, internal carbon gets attached there. The ethyl group just jumps from one side to the other. And now, what do we got? A new thing. So we have our C double bond O, double bond N, and the ethyl group, right? Because the nitrogen kicked in and made a double bond to carbon. We still have the double bond O, so that's all the N double bond O, C double bond O, and the ethyl's on the other side now. This has a name. It's called a isocyanate. Isocyanate functional group. It's a weird functional group. They are electrophilic, and as you might imagine, it's going to be attackable by stuff because you have the double bond to oxygen and the double bond to nitrogen. The carbon's fairly electrophilic and wants to be attacked. Okay. All right. So the textbook mechanism, the difference with my mechanism and the textbook mechanism is that they're combining the departure of the bromine and all of this stuff, and it's just a little harder to follow. I think it's pretty easy if you just imagine, okay, leaving group goes away, and then this little rearrangement happens from the acyl nitrene. That's the difference between the textbook mechanism. I like mine better. In reality, I think the textbook may be more correct, but this is a little easier to learn, I think. Okay, so now it gets a little more straightforward. Water is a nucleophile, and water is going to attack the carbon, and you have to decide, is our electrons going to go towards the oxygen or towards the nitrogen? And I'll just tell you they go to the nitrogen. The mechanism is really easy if you go towards nitrogen. Okay. Now I'm going to also sneak in a proton transfer. I'm going to go a little to the left because I'm a little worried about space. So I'm trying to go a little to the left there. Okay, so this attacks, pushes electrons onto the nitrogen, and I'm going to also do a proton transfer, essentially from the oxygen to the nitrogen. So that gives me HO, nitrogen, ethyl. Okay, so oxygen attacked the carbon, and that's where the OH is. But I also, just to save a little space in one step, I said PT, which assumed that one of the protons from the oxygen moved over to the nitrogen. Okay, this has its own funny name also. This is isocyanate. We went from nitrene to isocyanate. This thing's called a carbamic acid. Carbamic acid is the name of this thing. Okay, so we got the carbamic acid now, and we're very close to the product now. And to draw this thing is susceptible to something called decarboxylation, which basically means CO2 falls off. And I can draw this. I usually, it's a little hard to draw the exact mechanism for how this works. This is one way to draw it. And this is totally fine for quizzes and stuff. Just have your lone pair on oxygen, kick in, and break off. That's essentially making CO2. The only problem is our CO2 actually has an extra proton and the nitrogen has a lack of a proton. So to get around that, I just draw it that way. I'm like, okay, well, I made NH, another one of NH dot 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 minus, right? And then we have essentially CO2 with one extra proton. I flipped it around, whatever. It's CO2, right? O double bond C double bond O with that extra proton on there, and now I just grab the proton off or whatever. Okay, we're done. And that is the mechanism of the Hoffman rearrangement. Okay? So it's a pretty fun kind of multi-step mechanism. Base takes proton, makes N-, attack Br, make a bromo amide, I guess, N-bromo amide. Base takes the second proton. Now you have an N- thing with the bromine leaving group. Leaving group goes away. And then the weird rearrangement of the acylnitrene where the ethyl group jumps to the other side, makes the isocyanate, and then water attacks the isocyanate, pushes electrons towards the nitrogen, not towards the oxygen, but towards nitrogen. I just sneak in a proton transfer to help us not have to draw 1,000 things. Then we have the carbamic acid, which is like very close to product, and then we decarboxylate, so oxygen kicks in, breaks off, and makes kind of like a N- thing, and you have that CO2 thing. So some kind of proton, this is kind of like a proton transfer. I'm just drawing it out. N- grabs a proton and we're done. And net effect of the Hoffman rearrangement is loss of CO2, and the nitrogen just kind of, it's kind of like, if you think about it, it's really like those two atoms just go away. But it's through a complicated mechanism. Okay, that's the Hoffman rearrangement. Alright, Hoffman. Let's just show an example of it, just to see how this actually works. Benzene, alright, I'm going to do the Hoffman on this molecule. However, that's not the substrate for the Hoffman. The Hoffman's got to be a primary amide. So how do we make a primary amide? We have to first make a primary amide, right? And then we'll review how to do that. And then when we do the Hoffman, what are the reagents for the Hoffman? It's 3 of them. There's NaOH, Br2, water, or you could say Br2, NaOH, water, whatever you want. The main thing is that the double bond edge just goes away. So we had 3 carbons, 1, 2, 3. Now we have 2 carbons and the NH2. That's pretty cool. It's pretty easy to see, and tons of stuff going on there. Okay, but how do I make a primary amide? Well, how do I make any amide? The theme to making amides is usually OH is a bad leaving group, so make OH into a good leaving group, right? So it's maybe make it a good leaving group, kick off the leaving group. SOCl2, probably NH3. We don't necessarily need pyridine because ammonia, NH3, can be a nucleophile as well as a base, so no PYR needed. If you add pyridine, it's okay, it's a little bit wasteful. So yeah, ammonia can be a nucleophile and a base, so make an acid chloride and then the ammonia kicks off the chloride. Okay? Alright. Alright, we're very close to the end of the chapter, and we'll still have to probably continue next time, but I'm just going to introduce the last of the functional groups. And this is a little bit different than the other ones, but they have some similarities. Nitriles, chemistry of nitriles. So it's vaguely like the other carboxylic acid derivatives. It's got 3 bonds to nitrogen, right? It's like something like that, and yeah, like all of them are like, you know, 2 bonds to oxygen, 1 bond to nitrogen, or 2 bonds to oxygen, 1 bond to oxygen. But all I'm going to show this second is how to make them, and then we'll continue next time. This you know this stuff, so. Making nitriles. How do you make nitriles? Via SN2 is one great way to make nitriles. So one way to make them is SN2. So if I have like a suitable leaving group on a carbon, and I react with cyanide, like DMF. Often it's like sodium cyanide, like Na+, Cn minus, or just NaCN. All of those ideas are fine. Make it nice and linear because it's SP, right? Don't draw a bent nitrile if you can avoid it. Yeah, so the mechanism is that the carbon just kicks off the Br like that. Okay, so it's an SN2 reaction. The other way to do it, cyanohydrins. That's the other way that we've kind of learned to make nitriles. We've seen many times now, just take like a aldehyde or ketone or something and then react it with HCN. Maybe, yeah, probably HCN, NaCN. I think you can do the mechanism with just HCN. So, and it makes this thing that looks like an alcohol with a nitrile. Yeah, that's fine also. That's another kind of nitrile. All right, and we saw the mechanism a few times. Start by protonating, and then you have the RSCC, etc. And then basically Cn minus attacks the carbon, so you can finish that up. One more example, like cyclohexanone, HCN, NaCN. Also makes a cyanohydrin. So cyanohydrins are just nitriles with an OH group on them. So yeah, we have a couple ways to make nitriles. Alright, so next time we'll do the reactions of nitriles, which are actually really easy. It's nothing too crazy. We're basically done with this chapter now, and we'll just finish up next time, and then we'll jump into, I think, next chapter I think is amines.